Ladies and gentlemen, hello everybody. My name is Denise and I would like to speak about the verification of the code of an operating system. I work in Scientific Research Institute. I've been studying that since 2014. I also work with floppy drivers based on Linux kernel, so if you have any, please bring them. I'm really interested in them. I also work on Samsung ST Note T forum, and my another activity is connected with KSplice team. You can ask your questions online. Here's QR code or URL. And now let's get to the topic at hand. I try to do that briefly because the previous presentation was mostly about that. You have specification, and verification is the procedure that this specification is complied with. You can either set this program as a number of different equations and then check if these equations are true or false. For you to feel what that is and how does it work, when people say that something is verified, they believe that there are no mistakes and no errors there, which is wrong. There are some presuppositions which are in the foundation of this verification. They can be obvious and non-obvious. When you test, you assume that the programmer did not make any mistakes. You also assume that your equipment works at the expected level. When you create your security model, you also assume that the administrator will not leak all the keys. You assume all of that, and once you enumerate all these things, or at least think about them, what do you place this function on, this procedure on? And then you say, after this verification, we have mathematical guarantee that this code would work as expected. When all these assumptions are complete, there is always something left, unfortunately. Otherwise, we would not have formal verification fails. There is a wide range of projects connected with the verified code. You might have heard about some of them, like CompCert, C-Lite language compiler, or SEL4, marker kernel L4, Hackle cryptographic library, CakeML, verified implementation of machine learning. A lot of different projects, but each of them has some assumptions and presuppositions which are in the foundation of their procedure. For example, you can take the procedure of Certicos that these components are verified and these components are not verified, and we just assume that they work correctly. SEL4 has Q&A on their website, and the website says what is verified for these processes and what is not verified, what kind of architectures are verified and what kind are not. And to connect this presentation to the previous one, we do remember that SEL4 was not verified because of the complex work of the equipment. It's not only about the code itself, it's also about equipment. But the cryptographic parser of X500 certificates, there are some limitations on the parser, and the standard assumes that some fields in those certificates could be of variable length They checked the length and they said that this is the length of these variables and we will not make the field wider, and our parser will take only this width. Why does it happen? And what's the point? Why should people invest in this? It's not only about some ideal thoughts, some kind of romantic ideas. It's actually all very businesslike. There are tenders for delivery of certain software and hardware. You have certain requirements, you have certain standards and certification levels which this or that software must comply with so that it could be installed on this hardware. Most of the standards require only verified design model. The highest standards, the high-level verification model. But the verification of the source code, well, at least for now, there are any strict requirements. Sometimes it's just put like there that this should be done like this. But usually it's just tested. We don't understand that once we get enough success stories, this will incentivize people to add additional requirements to the open source, or rather source code verification. I would like to speak about a specific project. These processes happen everywhere around the world. For example, in Europe, there was a project, VESSEDIA, which ran for 3 years, since 2017 to 2020. And the idea was to check how can we apply the existing methods to the source code in a more or less critical way. Not the most critical ones, but we would like to certify it in a way at least, because the risks and threat levels are getting higher and higher. We used Contiki operating system. Frama-C was the verification tool. The Europeans believe that they develop this tool and they should use this tool. Frama-C and Contiki are developed by European counterparts. Frama-C is from India. Frama-C framework, ACSL specification language. You have a C code, one-liner, it's very simple, and people would say, well, you can divide by zero rather. But you can also do something else. If you guess the correct answer, you can get a t-shirt. So that's how specification looks like in Frama-C. You have a comment using a special language where you put the requirements to this area of the function. Here we say that b should not be equal 0. If this is fulfilled, then the function will work correctly, and we can return the result of this function, the result of all the input values which are true to the condition. Then we can prove that the results will comply with this or that standard. But this function cannot be proved correct. Once you run the tool Frama-C, it will change both specification, the source code, to some logical equation, and will generate a verification condition. And we must understand that the tool inside has different types of errors, and it knows about division by 0. It knows that it can be, but it doesn't know about the stack, for example. Well, there is no stack, at least here. So, do you know what else can it be and why there is no verification? What's the answer? Yes, it can go over stack. when int min, it will not go to int max because it's lower than 1. So you can either correct your code, increase the range of the return values, or change the precondition. You can also say that a should not be equal to int min. But once you specify this precondition, you will have to prove that a is never equal to int min at that point. So, speaking about the results of the project, you can look at this slide, the presentation, you can check all the URLs to see if these functions were verified or not. There were also contracts on cryptography and circle buffer, but they were not... Well, what I mean, the contracts. What exactly do we verify? For the circle buffer, we just verified the absence of runtime errors. But for the other case, we had a more complicated verification, which the code had to prove. And the most serious ones were for dynamic data structures. I tried to open the URL, and it's probably an example. Yes, you can see it on the screen. You have 3 lines of a function, but the specification goes down. You can see that in the comments with the @ symbol. This is the specification, and in order to prove a function, you actually have to fight the tool. I cannot call it otherwise, because what your solver runs and it doesn't prove anything, and that's why you start to write these asserts. In this case, you have some asserts which must be proved, but you also have some additional hints for solver. And you tell them that something else works here. And if they try to prove something, then it can use it as a hint. So for 1 line of code, you have 50 lines of specification. At least 2 errors were found in this list inserter and in the locator. But it was quite funny. People didn't really consider the second part as an error. It was so obvious that you cannot even think that it was an error. It was probably done on purpose. We do have to understand that the minimal contracts require as few these comments as possible. The lists made us prove some of the points manually because they did not work automatically. And what did I do? When you prove something once and you change the code to work with the verification tools, but you also change the code, and some of the functions which were proved before will not be proved later on. Some of these functions were removed. For example, when we were able to prove these new functions. The idea was how to create a single repository so that the verification would be near the code, and there is a change in the code, then you would rerun verification just to notify the programmers that this code is not proved anymore. Maybe you should check it and see to add something. In general, the schematic is as follows. You have a commit, you have a number of functions which were verified. If it refers to the commit, then we single out them in a single additional file. Then we use ACSL or other tools to fight the errors which were in the code and programmers did not include them in the final version. like Frama-C, for example, did not work correctly with bool type. And there was a transformation to change all these bools, all the indicators to functions. Program doesn't really understand these indicators or non-typed input commands. In the end, they verify what was before, what became after, and if something decreases or is not proven anymore, then there is a notification to the programmers, to the developers, that they have to improve the code. But as I said, at least I believe so, the main result of the VESSEDIA project was that they came to realize what Frama-C lacked. You have scientific studies, it all sounds fine, but once you start to work, this is not the best code to use. At least that's my personal opinion. At least it's worse than in Linux. And probably you could have different reports. They have them on the website, they look fine. But I believe, as a developer, that they started to improve verification tools. That's the most important result of their project. There is another project, Astra on parsec verification, which was mentioned by the previous speaker. Astra has its own verification module. It's a pretty small one with the closed source code, and it has two components. In order to pass the verification, it had a specific model using event B programming language. I will show how it looks later on the next slide. The model itself requires to be formal and to be proven by lack of contradictions. It also has different security requirements, and that verification should not violate these high-level security requirements. It was completely proven. There was also additional development for C language, for parsec, on compliance, but the compliance of the model is not formally checked. It's quite difficult to do, and I will try to explain later why. It requires pre-certification of the testing to see the compliance of the model and the implementation. And we also had to significantly improve the tools so that it could work with the kernel of the code. The only point is that this project started 3 years before the VESSEDIA project, and by that time many of the errors and mistakes were able to negotiate and get rid of. So what exactly I'm talking about? And why is this an abstract model? I think you will ask me about registers. I might have an answer, but what do we have on this slide? You have a number of entities, users, processors, files, lots of different entities, and you have a number of operations, like create a user. You have this event. This function has certain parameters, and you have the prerequisite for this function, when it can be performed and when it cannot be performed. For example, if this kind of user exists, then it cannot be performed to create a user. Or create user event must be created by some existing process. It must have a pre-existing process. If all these conditions are true, then in the end you see how to update this entity. It doesn't really matter. It can be event B and it can be TLA, other models, Contiki, Isabel. There are a lot of them. You can use them to prove these events. And this slide doesn't show some very important information. Well, here we have current user accounts and user profiles, which specify the global state of the entity. For example, this kind of user with this kind of tokens will never be able to have open active files or run processes by this user, or they will not be able to have a high level of security in the run applications. And after each and every of this operation, there is a proving that there was not any errors and mistakes, that these events are actually true. You can also go to the GitHub and check how they look like. LSM was already mentioned, that's why I will not go into details, but how does it happen when we speak about the kernel? We have requests, we have the basic checks of the processes, that we do not have any unnecessary garbage there, so to say. Then process starts to work, RVX and the users of the group and the rest. Only after that, LSM module is run. Then it tells the kernel, can they go forward, can they work with this process and use, I don't know, 33% of the resources, or they have to return an error. And the security module uses the internal logic, and they decide if they can do that or cannot. And they return an answer to the kernel. Okay, so you can understand that there could be different errors in the security model, some kind of misimplementation there. Maybe the kernel did not send the request in due time, or maybe it should request this check, but the kernel doesn't know about this check at all, which means that the LSM interface is not complete. And when verification starts, when we work with SSL, we take a look at the LOP model, but we have to start with the kernel, with the part of the kernel, not the whole kernel, because the whole kernel describes the function of the whole system, but we have to describe the specific checks in this some small area of the code, less than 5,000 lines. And here's a problem with the verification itself. The model is quite small, but there are about 400,000 lines of headers, so that they could generate all the verification conditions, and it takes about 20 minutes to generate this information. And you still cannot work with this information because nothing will be proven. The model is so huge that the heuristics will never understand where to go, what to address to, what to run. And here's another point. The more code you try to analyze, the more additional problems you would have. If you have A divided by B function, then you do not have any problems. But if you add additional elements to this function, then within the tool, you would have to model these functions. So you have lots of axioms inside this function. You expand your model, it becomes more complicated. So, for example, if you proved a single function before, it did not have any axiomatics before. But once you add this axiomatics, you add these bit functions, and you have different functions. You expanded the model, and it has been proved before, but it's never proven afterwards. You have to amend the code. You have to increase the number of timeouts, and you just have to hope that heuristics would prove this code. You know that it should, but it does not. But in reality, you should analyze different functions independently. And when you start to work on the specification for this specific module, in addition to these presuppositions regarding the software and hardware which you use for the formal verification, you have formal presuppositions. You have specific contracts, the requirements for the functions, and you do not prove them anymore for the functions which were before, which you already run with your kernel. You write the contracts and you say that this should work like this, and because you cannot prove like that, we can only test that. And for the tools to actually work, we had to enhance them significantly. Event B doesn't have register, stack, but not only that. their models are totally different. These models do not know about registers at all. They don't know about the stack. And the reason is simple. If they would add these events like byte memory, registers, stack, then you would have such a complicated model which you try to use, then nothing will be proven at all. That's why simplified things are used, so that, just to expand it a little bit, to support the costs from one structure to another, and to use these tools. But unfortunately, in the Linux kernel, this is widely used.
And to organize this working process of verification, what do we usually do? You know that we have a function, we have a modules, and we identify the most critical ones, and we set up priorities. This is what we have to do. And this is we have to do the first and second, and we write something in the log, and maybe we do not even have it in the model. And then the verification cycle, like I've mentioned, begins, and you begin to break down this code into separate functions or to a cluster of functions which do some kind of similar work. You write your specs, and you can prove and possibly to modify some errors or rewrite code for it to be provable. So then you finish writing and dropping it back to the repository. And for these things somehow to coexist, you need to organize continuous integration, CI, because you may have changed something in the function contract, and then boom, that particular location is no longer provable, where you change certain preconditions. Well, again, what I want to say is that this kernel module is evolving, and you have to support it. And one way or another, those specs within the projects have been rewritten like 3 times after rewriting the code, and they're trying to finalize the tools in such a way that you would avoid manual work and avoid any manual, improvements. That on the level of formal verifications, you may have some contradictions, and you may prove that 0 would be equal to 1, because you may require at the same time two conflicting, statements or ideas. I don't have much time. That's why right here we were assuming a map of how we are tracking those status of the formal verification and how we do this work. But again, I want to say that there is a video on the YouTube. You can check it out, and also you can see that here we have drawn different functions. Basically, it's a call graph which is marked differently depending on certain verification priorities. What we have done, what we have not, and the second demo element was of how we're pulling out the source code from the total code base, and we get the code which will be enough to compile the object module, and we keep the formatting, then we write specs and drop it back into the total code repository. And what we have been doing eventually into the certification lab, it's basically the status, what has and has not been done, what can or cannot be proved, and what has been proved in certain assumptions, some kind of reports which are being supplied with the documentations for the specs. And another, I would say, quite a solid achievement from my point of view would be that eventually we have the 2 code versions, the one which is developed by the developers and the second one, which we have been doing, begin to exist in the new repository. Because initially, the guys have been developing something like for 3 months. We've been doing some parallel work and trying to synchronize, and then one code version would get for certification, but in reality you have a totally different code version running up. But eventually things kind of merged, and we had to make some efforts to separate. I mean, not even to separate, but not to stand in the way of the developers with our specs, because sometimes it's like scary and they do not, it doesn't fit the code. And our stats is showing that about 2.5 code lines of specs per one CI strand of the code. The full verification takes about 6 to 7 hours. As for the connection, FNB, and the implementation, it's a separate moment, and it's difficult to to show the full congruence, because event B is describing of how the system should be functioning, but implementation is focused in one module, which is basically on the ALSM. You have different notations, different abstractions in the event B. In the kernel, you have users identifier, it's a whole number. And in the model, you have some files, and implementations have the index descriptors, etc. And right here, we've tried at some point to rewrite CCL, even B and C specs so that they would be using some kind of common names and would be similar to one another, and would also include into the SSL specifications certain levels which would reflect what is going on in the code of how it is written down in event B model. Well, the next project. And right here, I would like to say that it's an overload. It also has a source code. And here we did not write any specification for implementation, but what was important is to make a check whether this implementation is in line with the event B model. We've done it dynamically because there's a huge Linux source code volume, and you have to be able to repeat this procedure. Not like you've done it once and keep it up for a year, but you have to do it quite frequently. And you do it in the following way. You trace the systemic calls, which are being done in the real operational system, and you try to reproduce the results of this system to extrapolate it to the certain models. Well, if you have given access in reality, you're given access in the model. This kind of like a checkup is happening. And then there is a control of the code dynamic coverage and the event B model coverage to be able to to reproduce systemic calls on the model. You have to, in a special way, to specify it, and you have to add additional events which would be in line with the systemic calls. It's pretty close as it is happening with the arguments, and this kind of expansion, well, it requires model refinement. Basically, for each systemic call, sometimes it's easier, sometimes it is not, and you have to write some additional operation. But at some point in time, you can check some missed calls of your access control module. You can understand that at some point your LSM interface is not like really full. You're missing some hooks, and you can trace some logical mistakes in the access control module. All of this would be possible, but again, you have to remember that you have to do it with a certain level of coverage. You cannot guarantee, though, at any input data. How do we do it? Linux kernel with a module is being launched. In the test mode, we write this track of the system calls with the kernel technology k-crops with the net links. It's a socket from the user space kernel. We write it in the user space app, writing down these tracks and then transferring it into the mode which would be appropriate for the running on the model. And then we do the model animation. There is a Pro-B tool. You load into it a model which has been refined with the systemic calls, and then you load into this model a certain initial environment taken from the system. Yes, the existing users in the system and existing files when you run the tests and some other important things. And then you do your verification, what has been permitted in the system and what is maybe banned when you do the animation, on the model animation. Two simple situation when you have the, in both cases, banned, in both cases permitted, it's okay. But although you may have some nuances because you may ban it because there is the code of mistakes, AM something, or access could be in your model, like different type of mistakes. But it's okay. Another situation, the system permitted, but the model is saying no, the access should not have been given. And the last variation, that the system has banned it, but the model is permitting. And some cases are possible that the model is not modeling physical resources. It does not know what the physical memory limitations may be. It is not known that you can just rip out your hard drive or something malfunction. And in the real life, you may have this kind of mistakes, of course, and you have to check it. If it is a lack of memory kind of event, we can roll back the state on the model and then continue reproduction the way it was before. The only case when we could not do it, it was when we found in YAML have found some mistake. As for some practical conclusions that we can make based on some of these projects, and you're trying to understand where things are moving, and well, for the certification, it's important for them to have some success cases for the verification. And before introducing some additional kind of requirements, it is important for them to have some tools. And it's better that the developers of these tools would be nearby, so to say, in which case it makes sense of how to do this procedure. And actually, for the regulators, not only in Russia, but even in Europe, I think even in the US, it's working about the same. And the most successful projects for the C code verification, when the project has been developed for the formal verifications on the level of architecture, you put some requirements and some limitations, of course, and then it would be very simple to reproduce. But unless you have that, or you're working in a certain context like where you have certain coding of a certain data structures and interfaces, at least you have to do some simple things like testing, and you have to check the mistakes of the compiler. Sanitizers, of course, have to be employed, and it's good to follow some standards and do the code review, I mean, the architectural one. And whenever you do this kind of procedures, you will save a couple of burned out people who would be writing the specs manually and trying to prove something on the very bad performing code. As a matter of fact, we've seen it from experience. When the guys can see the well-written specs, they like it. It is not like, you know, a lot of certs, but when they are readable, you can just look, you can see, you can quickly understand what's going on from the documentation. It is also the experience of using some static analyzers in the kernel, and the marking actually is happening for its parts. And telling from experience, you have to change the code for specification when you try to prove something, and you have to give up many things which people may believe, okay, something from the byte arithmetics, but in the real life, in the real situation, whenever you test it, you would have to give it all up. And if you're writing a function which at the same time does kind of three things for several pages, and with the recursion going back to the code with the three inserted numbers, you do not understand what this code is doing, and your specification will be, if you have a bad code, your specification will be bad. It's not clear what you're trying to prove. And again, the most successful projects, in reality, most of them, of course, are the legacy code verification, and even the foreign researchers are saying it is very difficult to work when you have the two separate teams, and when the code is separately, specs are separately, you're trying to prove something, and the developers are making mistakes which seem to be non-critical. But what you said, something okay, is potentially possible. Well, when you have this exploit, come back to us. We do not want to hear about some potentially possible things. Well, eventually we arrive to a situation when the code and specifications are in the same place, and the specs developers, they have some bearings on how the code should be looking, because when I have to write 3 lines of specs per one string of the C code, I want to just slap people in the face and don't tell me what is possible or not. And the most advanced projects like Astra, which I've shown you on the first slide, those people who write in the code, they're writing the specs at the same time. And well, I guess this is all I wanted to say in my presentation, and you can evaluate it. Thank you for your attention. Open to answer your questions. Dennis, thanks for the presentation, and I want to ask you, This code verification and the methods of it, do they imply the simultaneous execution if you have a speed log, the atomic section or not? Secondly, I'm under impression that this kind of verification is such a heavy thing, which is difficult to replicate in the industrial scale for the small amount of code. And sometimes it may be more lightweight, and it's better than the static analysis, but not like it's like a heavy thing like a verification. So these are the two parts of my question. Speaking about the atomic sections, it's difficult. All these things do not even know what the multi-stranding is, and AVC developed by the Microsoft basically cannot use it in real life, because as soon as you have the multi-string, you have the more complex internal models. You are feeding it to solvers so that you prove the conditions of verification, which are no longer provable. And it's one of the big idea of how you can come up with such adequate model, but so that things will be working for you. So it's a whole multi-threading issues. All the bugs that we have been seeing with the multi-threading were happening because people who are writing specs have been looking at the code for too long, and then you can understand what the problem is. You can come up with some tricks and to describe them in the specs, but it's difficult, and it's like a quasi kind of modeling on the level of specifications, that is. Well, the second part of your question was, yeah, there are some other stat analyzers and methods, like it's a GARN or something, and they are workable. You can use them. You can build some specifying models on the code, and then to prove in these models some things. But you have to develop error models in them, and like you cannot be absolutely happy on this earth, okay? And there is no just a simple cookie cutter solution, and these are very complex tools, and oftentimes to be able to apply these tools, you have to have the guy who was developing this next to you, sitting next to you. You have to invest money into it for them to be able to grow up to such a level that they would be applicable on the industrial scale. As for the simultaneous implementations, I believe that in the contract analysis, they are trying to use this kind of methods like the kind of simple execution and abstract methodology. And well, speaking about the code, C code, even in Frama-C, you have some value analysis plugins which do this kind of abstract interpretation, enabling you to prove some things, and they're using these like ACSL specifications as like a nodes, and it's modeling. Okay, this variable right here is taking some kind of range of values. Then you upgrade it, and it's a different range of values. At some point in time, A divided by B, and it's trying to say that if abstract interpretation has shown that you have a 0 can never be here, it's impossible, then it considers that the requirements has been fulfilled as far as verification is concerned. Thank you very much. Thank you for the presentation. That's my question. You've been saying that there's no need to model hardware errors, and I want to specify, like, why don't we want to model them, and what's the whole point with this hardware? I'm not trying to say that there is no need. I'm trying to say that to model this kind of hardware mistakes, you have to model hardware, which is difficult by itself. And even ACSL4, if you'll open it up, they are writing you, okay, we do not verify this whole thing. DMA access is not verifiable, I mean mistakes, because you can connect a PCI device and there is no limitations, right? You can get an access, but what do you do with you bypass it with a verification, like Alexander was saying? You need a new level of abstraction. That is, you take YAML tables and tune them up so that certain areas of memory would not be written over. It's difficult. It's difficult to model a processor, and if we describe a certain requirements on the memory table, I can say that SSL language, expressive tools will be enough. I cannot just give it to you from the top of my head right now. Dennis, one more question. Oftentimes, verification is used for reliability proofing. Very often, you have some time limitations whenever we say about the real-time operational system. Can verification do something about this situation? Yes, it can, but not these tools which I've shown you right now. And yeah, to this end, you use a different toolbox. The same with the cryptography. These tools, they are not about cryptography because there are certain other properties for these tools which are used for these kind of tasks or these kind of problems. I guess I'm done. Thank you.